I'm live. Okay, can everybody see that? Good. All right. In case you're new here, I'm Ben Goodrich. I'm an employee of Columbia University. Columbia University has received several $1 million worth of grants to develop STAN. I'm also co-founder of STAN Group, which provides a variety of services to businesses attempting to use STAN according to Columbia University policy. Those two things together require such facts to be disclosed in public presentations. So what are we going to do today? First, we're going to learn how Bayesians predict future data. There is a persistent myth that if you're only interested in predictions of future data or data that you've held out as a testing set, then you should use data mining approaches. And it's true that the whole data mining movement arose due to people disagreeing with every assumption that frequentism makes. Frequentism assumes you're sampling from a population. People rarely do that. Frequentism assumes you're interested in the parameters of the model, and it tries to derive some, conditions under which its estimators make sense. There's a certain class of, problems where people are not interested in the models, but rather are not interested in the model parameters, but rather are interested in a particular function of the model parameters, namely the prediction of new data. And, frequentism was originally cooked up when collecting data was expensive at the margin. And before you do the analysis, you need to see what sample size would you need to go out and get to get a sufficient amount of power to test some hypothesis or something like that. Very little of that applies today in, internet context. One, data is not expensive to collect at the margin. It's practically free at the margin. Two, such people are not interested in testing a null hypothesis. All sorts of things like that that led, data mining to just reject all tenets of frequentism. But people took that way too far and said, well, data mining is the antithesis of statistics. But it's really only the antithesis of frequentist statistics. Bayesians can make predictions too, and it's actually going to turn out to be a richer answer than what the data mining techniques give you. We also want to start talking about vectors and matrices and probability distributions for not just two variables, but k variables. And those k variables are not going to be independent, so we can't just say, okay, the joint probability distribution is equal to the probability of k marginal distributions. That's rarely going to be adequate for what we're trying to do. But there's also a lot of models that are more easily and concisely explained in terms of vectors and matrices. So we want to have the ability to understand those models. And looking, into April, if you write your models in the STAN language in terms of vectors and matrices, that is going to be, more abstract. You can estimate more models with the same code, and it's easier for the computer to apply, some optimizations if you do things in terms of vector and matrix algebra than it is if you do everything in scalar algebra. So these are skills that we need to learn. Questions about those? Also, as you might have noticed, we have fewer people today than when we started with, and that happens every year. Good news is we have more people in this class than ever before. Bad news is we have more people in this class than ever before. But the other bad news is that a lot of people who were maybe interested in taking it have decided to do otherwise for whatever reason. And that, like I said, it happens every year. But particularly in the case of the QMSS, it's always disappointing, because what I'm trying to tell you is this, the things that we're learning in this course, the Bayesian approach, STAN, all that, is the most powerful quantitative method to apply in the social sciences or any other science or any other field where quantitative methods are applied. And the fact that there's a substantial portion of people in the QMSS who don't feel as if they're equipped to take a class like this, in some sense, is a failing of the QMSS. But it's something that we keep trying to work on. So for those of you who managed to convince yourself to stay, I think you should be applauded. It takes some fortitude to do that, but I would encourage other people to that you talk to look at the videos. If you're auditing, try to do as much of the homework as you can to really get as much out of it as the students who are taking it for a grade. All right. Okay, so suppose this upcoming summer, some number like 8, could be any number, doctors and nurses and whatever contract Ebola, so there's another outbreak. How would you figure out, based on what we did last time, what you believe about the probability that those people, medical professionals, will be cured by the drug that MAP biopharmaceutical makes? How would we figure out what that is? How would we go about starting to figure out what that is? Yes? So that's going to be part of it. So pretty much what we want, what's the probability mass function for these future data, given what we've learned from past data, which we did on Thursday. Okay, that's a start. Yes?
Get a function for the prior probability based on the Bayesian work we did last week, according to the previous outbreak.
Right, good. Use Bayes' rule. That's always the answer. You just have to figure out how. And here's how. So we want this probability mass function for the future data conditional on the K naught equals 5 successes we had in 2013 out of the 7 doctors and nurses who got Ebola during the last outbreak, and based on our original alpha and beta that we sort of loosely came up with based on the trials with monkeys. So this function is what we're seeking. And the how in this case is, I mean, I didn't invent it, but it's a pretty clever move. So we want this in black here. We have a binomial probability mass function for how many people survive conditional on P, which is the true success probability of this drug. We're going to multiply that by the posterior distribution for P conditional on our alpha and beta and the K naught and the N naught. And when we multiply those two things together, we get a joint probability distribution for P and K, where K is the sum of the number of successes in the future. So the Y tilde, that indicates future data, potential data. So we have this joint distribution for the true probability and the number of people who survive conditional on alpha star and beta star, where alpha star and beta star are what we derived last time. So now we have this joint probability mass function, but what we want is a marginal probability mass function for just the K, or the number of successes in future data. And when we have a bivariate probability distribution, we just have to integrate out, in this case it's continuous variable, the one that we don't want to leave the marginal distribution. So we have this binomial probability mass function. We have this posterior distribution for P, which we showed last time was beta distribution with parameters alpha star and beta star. Multiply those two things together, get a bivariate distribution of P and K, integrate out P over the sample space of P, and we're left with the marginal probability of getting K successes conditional on alpha, beta, and the past data that we've observed. So everybody see what we're trying to do there? Adam.
So if the red distribution on the right up there is the posterior distribution, and the stuff in blue to the left of it is the future data?
It's the PMF for future data.
Posterior distribution?
No, it's just future data. So we're imagining 8 people get Ebola this upcoming summer. The probability that they survive depends on the true success probability of the drug. So this is pretty much the same likelihood that we would have used for past data before we had human trials. So you could think of this as also the binomial PMF for, if we were in 2012 and we hadn't observed any tries with this drug on humans yet.
So in that case, that would be your prior?
This would be the likelihood, the probability of the data conditional on the unknown parameter. And then we would have a beta, for example, prior on P. But once we actually observe some human data, we update our beliefs. And so now we have a posterior distribution on P, and we're trying to work out what is our distribution for the number of survivals in future data if we were to use this drug.
This is essentially like a function in the unknown we want to solve for.
Yes, this is definitely a function.
So, yeah.
2 functions and an integral. So 3 functions in total. Yeah.
Can we use this like for any kind of prediction? Like,
Oh, yeah.
like for example, classification or clustering or whatnot?
Yep. It's just deriving your probability mass function for future data. Adam.
And so is all of this what, like the denominator of Bayes' rule? Like how does this fit into that?
So this is not Bayes' rule. This is just deriving a probability mass function. So it's simply manipulation under probability theory. However, the piece in red was obtained by Bayes' rule. We had past data, past beliefs. We updated our past beliefs to new beliefs. That's where the alpha star and the beta star come from. So this is a function of a posterior distribution. It also happens, it's a function of a posterior distribution that is in turn a function. So if we go to do that integral, we have 8 choose K that comes from the binomial PMF. We have 1 over the beta function evaluated at alpha star and beta star. Both of those do not depend on P, so we can pull them outside the integral. What's left is P to the power of K, 1 minus P to the power 8 minus K, P to the alpha star minus 1, quantity 1 minus P to the beta star minus 1. So we consolidate those together, and we have another integral that results in a beta function, now with arguments alpha star plus K and beta star plus 8 minus K. So what we have in the bottom line here is a probability mass function that represents our beliefs about how many people out of 8 will survive when they get Ebola this summer, conditional on the past data that we observed in 2013, and also the beliefs we had about the success probability coming into 2013. Yes?
So the beta function is the kernel of the beta A star and the beta star?
It's the integral. So this purple thing here, you could call that a kernel. The beta function is the integral of the kernel. Joe.
So is this a commonly used analytical technique where you
No.
take your stuff and you rearrange it to make up?
Oh yeah, that is common. The whole Bayesian thing is not particularly common.
But that particular analytical move is often
Yes.
useful.
So this second line here is what we're going to do over and over and over again, albeit not so much with calculus and algebra, but that's idea of, you know, this composition of, we have a probability mass function for future data. We have a posterior distribution that reflects the data that we've already observed. We want to compose those and then integrate out the unknown P in this case, theta in general. And that leaves us with a probability mass function for future data conditional on past data. We'll do that all the time. It's called the posterior predictive distribution.
Step 2 to step 3, what happens to the denominator?
There is no well, the red here is the function for the red there.
Yeah, I'm saying the denominator in step 2.
There's no denominator. This is not a fraction sign. This is a curly brace. I'm just saying the blue and the red are equal to the purple.
Oh, you're just explaining that.
Yes, with colors.
The second function is somewhat like a thing, like you actually estimate the second with the red function.
Oh yeah, we did that. We did that on last week.
Yeah, but like typically it may involve more complicated things like estimating the parameters by fitting a model.
Yeah, so it's the same idea, just more complicated and more reliance on simulations rather than math. But it's the same idea of composing the PMF for future data with the posterior distribution from past data and then integrating the unknowns out. Okay, so this distribution at the bottom is called a beta binomial distribution because those are the two pieces that went into it. In general, this idea of a distribution for predictions is called a posterior predictive distribution. Yes?
The very last step, the numerator has alpha star and beta star, and alpha and beta. Aside from last week, it was alpha star equals alpha.
Right. So this comes from integrating the purple thing here. So now the exponents on P and 1 minus P are alpha star plus K minus 1 and beta star plus 8 minus K. In general, the first argument to the beta function when you do this integral is everything that's not the -1. And everything on the second argument is, again, all but the -1. So what the amount of area under this curve is equal to the beta function evaluated at those two arguments. What we did to start with, this was our prior, before we conditioned on any new data. So all we had that sort of represented the state of our beliefs was alpha and beta. Then we updated those to alpha star and beta star. Now we're not really updating, but combining with this probability mass function for future data. And so the exponents get bumped up again. All right. So if we see this in R, we're just going to set alpha and beta to what I thought we said we set them to last week, but that might not be exactly correct. We have n equal 8. K is all the numbers between 0 and n. We create alpha star and beta star using the conjugate relationships that we had before. And we can create what's known as the posterior predictive distribution, what we predict on the basis of a posterior distribution that we obtained by evaluating this function, which is the R equivalent of the last line here. Because we've done this correctly, the sum of the posterior predictive distribution over the sample space for future data is 1. If you got anything other than 1, you did it wrong. Probability distributions for discrete random variables sum up to 1 over the entire sample space. And so we can compare that with what a frequentist might do, which is to just say, okay, I have a binomial distribution for the data. I'm going to plug in the maximum likelihood estimate for the success probability, which is just 5 over 7. And, you know, that's the probabilities with which I'll predict future data. And you can see that those are a bit different from the Bayesian posterior predictive distribution. So why is that in general? Yes.
That conservative, right?
Well,
Frequentist one.
yeah, I mean, they're smaller in the tails, bigger in the middle. Yes.
Because the K is relatively large in this total sample, it has 5 out of 7. So in the Bayesian inference, the confidence of curing that disease is higher. So it's concentrated more into the middle.
That's part of it, yeah. I mean, it could have been less concentrated. In this case, it is. But there's actually like a step more to the logic that results in sort of the Bayesian having a higher probability of like 1 or 2 or 10 or 8, whatever, than the frequentist one does.
It's a weighted average of the means between what is the prior and what is with the data.
Yeah, that's true.
So brings about, it spreads the distribution out more maybe.
Yeah. So why is the sort of the Bayesian distribution spread out more?
Because the moments are weighted averages essentially.
Yeah, we don't really have any moments here, but that is true. The moments in this case are weighted averages of the prior and the data. How sure are you that the true probability is 5/7? Exactly. Tat.
You started with a particular distribution that showed your beginning level of certainty. It's building in more uncertainty into your prediction.
Yes, so we still have uncertainty in our predictions. That comes from both our uncertainty, you know, about the future. You know, it worked decently on the past people. It may not, like slightly different strain of Ebola or whatever, it might work worse on future people. But this point about uncertainty is very important. No one is sure, not even the frequentist, that the true probability is 5/7. But the frequentist plugs in their best guess and goes from there. Whereas the Bayesian approach doesn't put in the best guess, it puts in the posterior distribution, which accounts for our uncertainty, reflects our uncertainty about what the true cure probability is. So we don't, you know, it's somewhere like the mode is around 5/7, or the mean and the median are perhaps close to 5/7, but we don't know that it's 5/7. And so we have to propagate our uncertainty about the cure probability to our distribution of beliefs about future people being cured. It might very well be the case that this drug is not particularly effective and we just got lucky in 2013, in which case, you know, there's not as good chance that people will survive the next sort of outbreak of Ebola. Yes?
So you have a large sample size, for instance, it's 5, 7, it's like million data, but Bayesian and frequentist, they converge.
Yes. Right. So if we were sure, if the Bayesian was essentially sure, you know, based on past data, that the true probability was 5/7 or any other number, then, you know, we're plugging in a very concentrated posterior distribution into the posterior predictive distribution. And we get a very similar answer when the frequentist does the same thing. But, you know, as this reflects, and even more so with the data mining thing, non-Bayesians are basically going to systematically underestimate the uncertainty in the predictions when you plug in one particular estimate as if that was the truth. But you really had no basis for doing that, particularly with a small amount of data. And that's why, you know, frequentists can't be trusted with anything important, because they're going to systematically underestimate the probability of stock market collapses and, you know, global warming, all these things that have like a huge amount of uncertainty, you know, associated with them. If you just sort of plug in your best guess and then work out the implications, those implications are not going to reflect your uncertainty about the parameters that you're trying to estimate. And this happens over and over and over again. So these posterior predictive distributions are sort of a uniquely Bayesian thing, where you can put a probability distribution on any future event that's consistent with your beliefs based on the data that you've seen so far. Adam.
So this is kind of why the Princeton election predictor guy said it was like a 99.9% chance.
Yeah, on the New York Times. It's part of the reason going into that. People being, it's easy to be overconfident if you're not Bayesian, because you just have these like one number point estimates and you sort of mentally forget that you weren't sure that was the right answer. You couldn't have been sure that that's the right answer. So the posterior distribution reflects the entire state of your beliefs. And posterior distribution is a function. You need to put the whole function if you're going to evaluate, you know, something like the predictions, rather than just one point from that sample space as if it was the truth. So if you're going to reduce a function to a single number for whatever reason, you don't have to, but if you're going to, do that at the absolute last step. Don't reduce a function to a particular number in the middle and then plug that into another function that, you know, yields a distribution, because you'll get a distribution that's too close to the false truth that you've put in. All right? Yes.
I'm not sure whether this question even makes sense, but since the frequentist assumes that this process follows a binomial distribution, and we've created a beta binomial distribution, is the beta part of that somehow acceptable as quantified uncertainty?
Yes. So this binomial distribution, I mean, the Bayesians don't own that. It's the same binomial distribution the frequentist is using. The frequentist is just plugging in p hat, whereas we're essentially plugging in the posterior distribution for p. And Bayesians do own the posterior distribution. So it's really a question, are you going to put in a maximum likelihood estimate and just call it a day? Or are you going to put in a posterior distribution that reflects your entire beliefs about p, and then integrate p out to get the last line here, which is a beta binomial PMF. So both people are using binomial, but only the Bayesians are using a beta posterior, and the frequentists and the data mining people are using a plug-in point estimate. All right. I can move on to vectors. Surely the specter of vectors will induce someone to ask more questions about the posterior predictive distribution. No? All right, ask them on Courseworks or Piazza. Okay, so we're going to start to think about collections of random variables collected in a vector. So in my slides and, you know, the rest of the semester and whatnot, if I use a boldface letter, and I actually did on the homework, like, you know, boldface X, that's going to stand for a vector. And in general, when we talk about, or when I talk, most people talk about vectors without saying specifically the orientation. We're thinking about a column vector if in that context it makes any difference. So a vector is a collection of either constants or, more interestingly, random variables of length k. So this boldface X contains k scalar values on some concept X. Like I said, we usually think about columns as being oriented vertically, but the transpose operator, which I will use T superscript, sometimes you'll also see people use like a prime symbol. It's like a little short diagonal line to indicate the transpose operation, which changes a column vector to a row vector or changes a row vector to a column vector. But unless otherwise specified, we'll be thinking about vectors as being column vectors. And the T function in R can be used to transpose not only vectors, but matrices, which we'll see in a second. So vector is really just a collection of scalars. It's like a container. But there is a distinct algebra for vectors. And this is most clear that this is something different from scalar algebra if we consider vector multiplication. So in order to multiply two vectors together, they need to both be of the same length, in which case we can define vector multiplication, which is also sometimes known as the dot product, the inner product, vector product, many names for the same thing. This is the product of X transpose and Y. And it's simply defined as the sum of the pairwise products between the elements of X and Y. So you take the first element of X, multiply it by the first element of Y. Add that to the product of the second element of X and the second element of Y. Add all those pairwise products up over all k elements, and you have the vector product of two vectors. So the product of two vectors is a scalar. So that's the main thing that is different about vector algebra. So in R, you can implement vector multiplication using the percent sign star percent sign operator. That's something different from just the star. There's also a function in R called crosspod that also does vector product of X and Y, where X and Y are two vectors of the same length. So although there is vector multiplication and it's a very fundamental operation, there really is no such thing in terms of the algebra as vector division. So we'll hopefully clarify that in a few slides. But one of the most common constructions for vectors and whatnot is to take a vector and multiply it by itself. And so if the vector product of X and Y is just the sum of the pairwise products, and Y happens to be equal to X, so now you're just, the pairwise products are the squares of the elements of X, and you're summing that up over all k elements in the vector. You have a sum of squares of X. Okay? Hopefully most of you have seen this before. So one application of this vector idea, and I think someone asked about it like the first day, which was way too early, but suppose an outcome can take exactly one of k values. If k was 3, we might have like a survey question where the possible answers are no, maybe, or yes. And so we can have represent that response in terms of a vector. So if the person says yes, like the way surveys it'll just be a column and it'll have like the word yes, or worse, it'll have the number 3 there. But in terms of thinking about this mathematically, we want to think about that as a row vector or a column vector. It doesn't really matter that much, where the third element is 1 and the other 2 elements are 0. So this sample space, we're thinking about it in terms of vectors. We're thinking about a vector that has exactly one of its elements equal to 1, and all the other ones are equal to 0. So you can't have 0, 0, 0, nor can you have like 1, 0, 1. You give exactly one answer. So mutually exclusive and exhaustive categories. So this idea of a categorical distribution is just a generalization of the Bernoulli to sample spaces that have 2 or more elements, and those can either be ordered or unordered. And if the categorical distribution is a generalization of the Bernoulli, the multinomial distribution is a generalization of the binomial, and it's the sum of n independent categorical variables that all have the same parameter vector p, and the probability mass function for a multinomial distribution is written this way. N factorial, where n is the number of observations or the number of independent categorical variables being summed up. And then we have a product of p, the kth element of p raised to the power of x, divided by x factorial in the denominator, multiplied over all elements of k. So I didn't write this on the slides here, but there's a function in R called prod, P-R-O-D, which is just like the sum function in R, except rather than doing addition, it does multiplication over a bunch of elements in a vector. So the probability mass function for the multinomial distribution is defined this way. So this x vector is a vector where each element is an integer, and those integers are the number of times category K was realized. So if you do a survey of 100 people or whatever, there might be 30 people who say yes to your survey question, in which case 30 would be like the last element of X. And some people said maybe, some people said no. So each X is going to be an integer that's non-negative, but or each xk is going to be an integer that's non-negative. The vector x contains those counts, and those counts sum up to n, the number of categoricals being summed up here. The parameter p is typically unknown, and you're going to want to estimate it. This is a parameter that's basically a vector representation of a probability mass function. It's a vector with non-negative elements that are constrained to sum up to exactly 1. So if the possible answers are no, maybe, yes, the 3 elements of P are going to be the probability that someone says no, the probability that someone says maybe, and the probability that someone says yes. Since those are mutually exclusive and exhaustive, those have to sum up to 1 in addition to being non-negative. So this is one way in which vectors come up as in probability distributions. And I didn't write it on the slide here, but it can easily be shown that the expectation of x, so first of all, the expectation of a vector is equal to a vector of expectations. And the expectation of x under a multinomial distribution is p. So we have like all these zeros and ones and stuff. If we do the expectation operator, we get p in this case, just the same way that like when we did Bernoulli, the expectation of that was p, but that was just when we had 2 possibilities. Now we have more. So that was for the categorical distribution. The expectation of a multinomial distribution is n, the scalar, times p. So just bump it up by a multiple of n. All right. So we'll see this in a couple weeks when we start getting into some real social science. Okay, we have this parameter p how can I express my prior beliefs about what the elements of P are in terms of a probability density function. And the one that is the most used is known as the Dirichlet distribution. And the Dirichlet distribution has the following probability density function. Again, it's going to be some constant that depends on another parameter, alpha, multiplied by the product of each element of P raised to the power alpha k minus 1. And you might say, well, that looks a lot like the beta distribution that we dealt with before. And in fact, the Dirichlet distribution is a generalization of the beta distribution to the case when there's more or at least two categories. In other words, a beta distribution is a Dirichlet distribution when k is equal to 2. So this normalizing constant out here is known as a multivariate beta function. It can be represented like this with these gamma functions. And the gamma function is just another weird integral that has like some amazing properties and whatnot, and is implemented in R with the symbol name gamma. So the gamma distribution specializes to the factorial function when its arguments are integers. So z factorial is equal to the gamma function evaluated at z minus 1. So you can sort of think of the gamma function as a generalization of the factorial. You can also use the gamma function to prove like the weird fact that you probably encountered in high school that 0 factorial is equal to 1. But it's just an integral, an area under a curve that can't be represented in more fundamental elementary math functions. So if that's the PDF for the Dirichlet distribution, what's the expectation? The expectation is of the ith element of P is equal to alpha I, which you supply, divided by the sum of the alphas. So if you just sort of write this as, you know, alpha I as a proportion of all the alphas, that is the expectation for PI under a Dirichlet distribution. The mode doesn't always exist, but it does if alpha I is greater than 1. You can also see that if all of the alphas are equal to 1, then we're just raising P to the power of 0. So we just multiply 1 by 1 by 1 by 1. And in that case, the PDF is going to be constant over the sample space of P. And the sample space of P is sometimes known as simplex vectors. So we'll encounter that word again when we do stand code. And just like the beta distribution is conjugate with the binomial probability mass function, the Dirichlet distribution is conjugate with the multinomial probability mass function. So you can also work out what Bayes' rule implies analytically if you sort of combine those two functions together in the numerator. But all these conjugate relationships are very special cases. So we can cook up examples like maybe 15 or so where we can solve this analytically, but that's 15 out of like an infinite number of posterior distributions that we can think about, but we can't really work out analytically. So next week we'll have to start, or 2 weeks from now, thinking about how we can do that with simulations of random numbers rather than a bunch of algebra and calculus. All right. So just more of the like hundreds of distributions that are out there to sort of keep in mind. Okay, matrices. So matrices are collections of vectors that all have the same length. So a matrix is a two-dimensional container. You can think about it as a collection of column vectors, or you can think about it as a collection of row vectors. And the convention is to write matrices with capital boldface letters. So capital boldface X is a structure like this, where we have K rows and P columns, and each element in that two-dimensional container holds a scalar that has to be in general indexed by 2 indices. The first index is going to pertain to the row in which that element is located, and the second is going to pertain to the column in which that element is located. So if I write x sub p, I'm referring to the pth column of x, whatever number p is. And if I write x transpose k, I'm referring to the kth row of x. Otherwise, it would be a little bit ambiguous as to which vector I'm talking about. And the transpose operation can be applied to matrices in just the same way it can be applied to vectors. It's basically repeatedly transposing every vector in the matrix, such that if you transpose a matrix, you're switching the row index and the column index for each element in the original matrix to obtain a new matrix. And we say that X is a symmetric matrix if it's equal to its own transpose. So switching the column label and the row label, if that results in the same matrix, then we say the original matrix is symmetric. All right? Some vocabulary here. Okay. Multiplication of a matrix by a scalar is entirely straightforward. You take every element in that matrix, multiply it by a common scalar, and you get a new matrix that has the same dimensions. And this is multiplication of a matrix and a scalar is commutative. And basically, a vector is just a special case of a matrix that has one row or one column, depending on whether it's a column vector or a row vector. You can multiply a scalar by a vector and you get a vector of the same length that contains the product of each element in the vector and the scalar. So this is pretty directly analogous to what you would do in scalar algebra. But multiplication of vectors is and matrices and whatnot is a different thing. Another thing that is pretty intuitive is addition and subtraction of 2 matrices. So this is only possible if X and Y both have the same dimensions. So in this case, they both have K rows and P columns. We can define the sum and the difference of X and Y as just the element-wise sum or difference of the elements in each of those 2 matrices. So that hopefully makes it clear why you can't add 2 matrices that have different numbers of rows or different numbers of columns or something like that, because there would be some piece of one of the matrix that's left over and doesn't have a corresponding thing to add to it or subtract from it. So they do have to be the same size. Again, vectors are just a special case of matrices, so we can add or subtract 2 vectors that have the same length. That's fine. Something that strictly speaking shouldn't be defined, like addition or subtraction of a scalar from a matrix. Most computer software will just interpret the expression matrix X minus scalar A as matrix X minus scalar A times matrix J, where J is a matrix that's the same size of X, but all the elements of J are 1. So you multiply A by a matrix that's all 1s, you get a matrix that's all A's of the same size as X, and then you could subtract that from X, or you could add, same deal. So that is sort of an abuse of notation, but almost all computer software will interpret matrix plus scalar in a way that could have made sense. All right. Rolling along, there is such a thing as element-wise multiplication or element-wise division of matrices. This is technically speaking not part of linear algebra, which may only make sense to you if you've taken like many semesters of math. But like the definition of algebra does not include these element-wise operations. They just happen to be pretty convenient a lot of the time. So software will often permit them. So if you have two matrices of the same size, you could define element-wise multiplication or division in the same way that we define element-wise addition or subtraction. You just do the operation on every pair of the elements of x and y. But when we do so, you need to emphasize that this is element-wise multiplication or division rather than just plain matrix multiplication, which is something different and it's part of linear algebra. This is not. So again, software will do this for convenience, but mathematically, this is sort of not kosher. All right? But it happens all the time. So what we mean by matrix multiplication is an extension of what we meant when we said multiply two vectors together. So here's how matrix multiplication works. If you have one matrix, let's call it X, that has k rows and m columns, and you have another matrix called Y that has m rows and p columns, then we can form the matrix Z as the matrix product of X and Y. Z is going to be a matrix with k rows and p columns, and the elements of Z are again going to have two indices indexing them. So the kp element of Z is defined as the vector product of the kth row of X and the pth column of Y. So we take the kth row of X, vector multiply it by the pth column of Y. We do that for all rows of X and all columns of Y, and that's going to exactly fill up all the elements of the Z matrix, because the Z matrix is going to have k rows and p columns. So let's say that again without as many parenthetical comments. X is a matrix with k rows and m columns. Y is a matrix with m rows and p columns. Their matrix product I'll call Z. Z is a matrix with k rows, p columns. Each element of Z is a vector product of some row of X and some column of Y, where all the unique products of the rows of X and the column of Y are represented in the elements of the Z matrix. So that's another thing in R that you can do with the percent sign star percent sign operator. And that's basically an extension of vector multiplication to the case of matrices, where we think of matrices as being a collection of vectors that all have the same length. One of the things that, if you come from a scalar algebra perspective, you find initially confusing about matrix multiplication is that matrix multiplication, unlike scalar multiplication, matrix multiplication is not commutative. So X times Y is not equal to Y times X. And in general, that Y times X might not even be defined, because in order for matrix multiplication to happen, the matrix on the left has to have the same number of columns as the number of rows in the matrix on the right. So if I tried to multiply Y on the left and X on the right, then that would have P matched up with K, which wouldn't work unless K and P were the same number. So we say that two matrices are conformable for multiplication if the one on the left has the same number of columns as the one on the right has rows. Otherwise, they're not conformable for multiplication, and matrix multiplication is not defined in that case. However, although matrix multiplication is not commutative, the transpose of X and Y is equal to the product of y transpose and x transpose. So that can be proven. One of the most common constructions that you've probably seen before when you studied like ordinary least squares is the matrix product of matrix of predictors, let's say x, and a vector of coefficients beta. So if beta has the same length as, so I probably should have called this p, but if beta has the same length as x has columns, then x and beta are conformable for multiplication. And x times beta, we just form it by taking each row of x, multiplying it by the vector beta. That's going to be a scalar. We stick that in the result. We do that for all rows of x, and we get a vector that's n by 1. And each element of that vector has the product of some row of x and beta. And beta is common for all of those. So you can write that in various ways. You can write it as a vector product. You can write it as a sum of pairwise products. You can write it if you really want to, but this is more verbose, with like a dot, dot, dot there, and it's just all scalar algebra. But it all amounts to the same things. You're taking each element of x, multiplying it by the corresponding coefficient in beta, summing that all up to get, something like y hat, if we were talking about ordinary least squares. But this is sort of the most concise way that we can illustrate that operation is with, x times beta. So that's a whole lot less writing, which you'll come to appreciate. But you've got to be able to understand what the x times beta operation results in. All right. So questions about matrix multiplication and or how it's distinct from element-wise multiplication. Element-wise multiplication is more or less like addition or subtraction. But element-wise multiplication requires x and y to have the same size exactly. Matrix multiplication just requires the number of columns in the matrix on the left to be equal to the number of rows in the matrix on the right. Their outside dimensions, those can be anything. Questions? Okay. So like we said, a row vector is basically a matrix with just one row. A column vector is basically just a matrix of one column. So another common construction, not quite as common as the common constructions that I referred to on previous slides, is if x and y are both column vectors of the same length, we can define what's sometimes known as the outer product. Is really just a special case of matrix multiplication. Here, x, which is k by 1, multiplied by y transpose. Y transpose is 1 by k. So those are conformable for multiplication because x has one column and y transpose has one row. And that's going to result in a matrix, we might call it Z, that has k rows and k columns. So you can think about this as scalar multiplying each element of x by y transpose, or you can equivalently think about it as scalar multiplying each element of y times the vector x and filling it up column-wise. Either way, you get a k by k matrix whose elements are every possible pairwise product of the elements of the x vector and the y vector.
Are those should be yk instead of yp?
On the right here?
Yeah.
Oh, yeah.
And the
Yeah.
middle, and the middle one.
Yeah. So p is equal to k here. I could have done without the p's. Thank you. So this is implemented by the outer function or the t cross prod function in R. But it's really just a special case of matrix multiplication with a k by 1 and a 1 by k, where p is equal to k. All right. So there's technically nothing new about outer products. They just differ from inner products, which was defined as x transpose times y. That resulted in a scalar. X times y transpose results in a matrix. Okay, so some matrices are more special than others, particularly those that have patterns of zeros, in their elements. So in this case, we have a matrix that's k by k. We call that a square matrix, a matrix that has the same number of rows as it has columns. A matrix is called triangular if it's square, and a lower triangular matrix, ironically speaking, has zeros in its upper triangle. So I'm just going to draw one of those. For a lower triangular matrix, all those can be anything. But the ones above the diagonal elements, those all have to be 0. Okay? So lower triangular matrix is a square matrix that has all zeros in the upper right triangle. Conversely, still weirdly in my opinion, upper triangular matrix is the transpose of this. So you flip all the row indices and the column indices. So now the non-zero elements are going to be in the upper right triangle, and everything in the lower left triangle is 0. That's known as an upper triangular matrix. So the lower and the upper, those refer to the non-zero elements. Now, some of these can be 0 as well, but they don't have to be 0. What makes a lower triangular matrix a lower triangular matrix is that all the elements in the top right triangle above the diagonal must be 0. Everything in the bottom left, it's optional as to what it can be. Okay? And I put up here trapezoidal. You can extend the idea of a triangular matrix to a non-square matrix, like one that has more rows than it has columns, or more columns than it has rows. But we don't really encounter these trapezoidal matrices that often. But I think they were mentioned in the book. A diagonal matrix is a square matrix that is both lower triangular and upper triangular, which is to say, like, all these are 0 too. So the only thing that's allowed to be not 0 are the elements on the diagonal. So diagonal matrix has zeros everywhere except where in the k elements where the row index and the column index are the same. So that's what we call the main diagonal of a matrix. Main diagonal of a diagonal matrix can be anything, but all the off-diagonal elements in the lower left and the upper right triangle must be 0. All right? Further specialization of this idea, the identity matrix is the diagonal matrix where all of the diagonal elements are 1. So if we have a diagonal matrix, all the elements on the diagonal are exactly 1. That is the most special matrix, and that is the identity matrix. It has a special symbol, boldface I. You'll also sometimes see it like I with a subscript K under there. That just means it's a K by K identity matrix. But usually the size of it will be clear from the context. And the identity matrix is basically the matrix analog of the number 1, the scalar number 1. So scalar number 1 is, again, one of these like top 5 most important numbers in history, along with E and pi and 0. So this is, you know, one of the most, it is the most fundamental matrix, and it operates a lot like the number 1 does in scalar multiplication. And by that I mean, if X is a square matrix and I is an identity matrix that's the same dimensions as X, then X times I is equal to X. Also, in this special case, I times X is equal to X. So in general, matrix multiplication is not commutative, but in some special cases, it turns out that way. But it's not generally true, so don't bank on that. But the identity matrix is like the scalar number 1, and that you can multiply some matrix by the identity matrix, and you get the matrix you started with. Just the same way you can take a scalar, multiply it by 1, and you just get that scalar. Okay? So as long as X and I are conformable for multiplication, then, you know, X times I is equal to X. And that's a very important fact. Another special matrix is the 0 matrix. That's a matrix or a vector that has zeros everywhere. Okay? So I defined that matrix J earlier. That was a matrix that has 1s everywhere. That is sort of special. It doesn't come up. But one thing that people get confused a lot is they think a matrix that has 1s everywhere is like the scalar number 1, but it's not. The matrix that's like the scalar number 1 is the identity matrix, which has 1s on the diagonal and 0 everywhere else. Okay? That's the identity matrix. That J matrix is just a matrix with all 1s in it. Doesn't really have a special name. Some people call it a 1s matrix, but that is not an identity matrix. So questions about any of these special matrices? Yep. Okay. So what happens if we take a diagonal matrix D and we multiply it on the right by some matrix X that's conformable for multiplication with D? So when we multiply a diagonal matrix by some matrix, what happens is we get a matrix that is the same size as X, where each row of X is scaled by the corresponding diagonal element of D. So we take D times X, and this is a diagonal matrix, and we have all these row vectors in the matrix big X. What results is a matrix that scalar multiplies D11 by the first row vector in X, and scalar multiplies D22 by the second row vector in X, all the way down to the kth row vector in X. So diagonal times matrix scales up each row of the matrix on the right when you get the resulting matrix. Conversely, the product of any matrix that has k columns with a k by k diagonal matrix D is going to scale each column of X by the corresponding diagonal element of D. So we get, you know, X1 times D11, second column of X times D22. Bind all those together, we get a new matrix that is the same size as X, but each of its columns has been the result of it being multiplied by the corresponding diagonal element of D. And so if you have a particular diagonal matrix, the identity matrix, and you multiply that on the left or the right by X, then you're just multiplying the rows or the columns by 1, and you get the same X matrix that you started with. provided that they're conformable for multiplication. So multiplying by a diagonal matrix is, you know, a little bit easier to understand than multiplying by just an arbitrary two matrices together. But we can still understand pretty easily what the product of two regular matrices is. It's just cranking through a whole bunch of vector products. And honestly, like, the computer does that for you if you just use the percent star percent sign. Questions about diagonal products? Okay, last one for today. Matrix inversion. So if X is some square matrix, which is to say it has the same number of rows that it has columns, then we have a concept known as the inverse matrix of X. So presuming the inverse of X exists, which it almost always does, we're going to denote this matrix X superscript -1. And the inverse of X is the unique K by K matrix such that if you multiply X by the inverse of X, you get the identity matrix. It's also true if you multiply the inverse of X by X, you also get the identity matrix. So this idea of an inverse matrix is basically the matrix that we can multiply X by and get the identity matrix. And the reason why we might want to do that is because the identity matrix functions like the number 1. So, you know, in scalar algebra, you know, let's say you have like some number B and you want to multiply like both sides of the equation to get rid of B. So you can multiply by 1 divided by B. And then like one side of your equation is equal to 1. And then you do that to the other side of the equation and, you know, you get something else. But basically to cancel out the scalar B, you can divide by B, provided that B is not 0. Or you can think of division as being multiplication by the reciprocal of B. So we do that in scalar algebra a lot to make things on one side of the equation equal to 1. When we have a set of matrix equations, we're going to want to multiply one side by the inverse matrix of something in order to cause one side of the equation to be the identity matrix, which is really like the simplest matrix to work with. And this happens when you derive ordinary least squares like X transpose X inverse X transpose Y. The reason why there's an X transpose X quantity inverse in there is we wanted to isolate the OLS coefficient vector to, you know, get rid of what it was multiplied by multiplying by a certain inverse matrix, and then now it's multiplied by the identity matrix, and so it just comes out the regression coefficients. You don't really need to worry about how software finds like what the elements of X inverse should be. There's algorithms for that. They're not particularly enlightening. It's relatively, it's easy for a computer to do. It's just number crunching. It's easier if to imagine how that works if the matrix is diagonal, in which case the inverse of it is going to be another diagonal matrix with reciprocals on its diagonal. It's pretty easy if one of the matrices, if X is triangular. But again, this is just really a computational thing. What we really want to understand the concept of matrices resulting in a product that yields the identity matrix. So like I said, there's no vector division or matrix division, but there is matrix multiplication by an inverse matrix to get the identity matrix. So there's some other properties about inverses that are listed in the book and good to know. So if you have two square matrices, X and Y, the inverse of their product is equal to the product of their inverses, except in reverse order. Also, the inverse of a transpose is equal to the transpose of an inverse. Things like that, you know, are properties of this inverse. So that's all the time we have for today. We'll pick it up Thursday using these idea of matrix inverse when we talk about the multivariate normal distribution, which is a generalization of the scalar normal distribution. And it's, you know, just like the scalar normal distribution is very important, the matrix normal distribution is also going to be very important too. Okay, keep posting questions on Piazza, whether they pertain directly to the homework or not. If they do pertain directly to the homework, be sure to ask them in for instructors only mode. Okay, stop broadcast.